What if one of the most sacred constants in physics, the speed of light, isn't constant at all? For over a century, c has been treated as unbreakable law, the backbone of relativity, space-time geometry, and even the clocks we use to measure the universe itself. But now, a new 2025 analysis gathers decades of gamma-ray data and pits it against this cosmic assumption, asking whether light truly travels the same speed everywhere, forever. The speed of light in vacuum, roughly 299,792 kilometers per second, has always been more than a number. It's the rulebook that tells nature how to behave. If c wobbles even slightly, then physics as we know it starts to shake. Modern telescopes let us test questions early scientists couldn't even imagine, tracking photons across billions of years to see if they keep pace or drift. So, what if constant c isn't constant at all, and the universe has been hinting at it for decades? Imagine being a physicist in the late 1800s. The universe seemed full of waves, sound waves, water waves, even light was believed to be a wave. And waves need something to travel through, right? Enter the ether, an invisible cosmic medium believed to fill all of space, a kind of universal ocean that light rippled across. If Earth sailed through this ether, then the speed of light should appear slightly different depending on whether we were moving with the cosmic flow or against it. It was elegant, logical, and completely untested. To settle the debate, Albert Michelson and Edward Morley built one of the most famous experiments in scientific history. They split a beam of light into two perpendicular paths, sent them speeding around a mirrored racetrack, then recombined them to look for interference, tiny timing differences that would reveal if light traveled faster in one direction than another. It was a brilliant idea. If ether existed, light should experience a headwind or tailwind, just like a boat moving through water. But when the results came in, nothing. No shift, no difference, no trace of the ether at all. This null result became a turning point, shaking 19th century physics and quietly opening the door to a new perspective. Maybe light doesn't need a medium. Maybe its speed is the same for everyone, everywhere. The constant c idea wasn't born overnight, but Michelson and Morley handed future scientists the spark. Yet even with this landmark result, the story was far from over. Later revolutions, quantum mechanics, curved spacetime, cosmology, would reawaken the question that 1887 thought it buried. If light speed defines reality, what happens when reality itself bends? Einstein enters the scene not as a myth, but as a man confronted with a universe that refused to behave the way textbooks said it should. The Michelson-Morley experiment didn't just fail to find the ether, it cracked open the foundations of classical physics. If light speed really didn't change, no matter how Earth moved, then time and space themselves had to be questioned. Scientists tried to patch the theories they already had, but Einstein did something far bolder. He threw away the old assumptions and started from two simple postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is constant for all observers, no matter how fast they move. These were not tweaks, they were detonations. If c is constant, then clocks tick differently for observers moving, relative to each other. Lengths contract, mass increases with speed. Time and space fuse into a single woven fabric called spacetime, and light becomes the ultimate ruler of that geometry. This was not convenience. It was necessity. Make light's speed variable, and relativity collapses. GPS satellites fail. Particle accelerators stop matching predictions. The universe, instead of running on elegant mathematics, becomes chaotic and inconsistent. In Einstein's vision, c isn't just a number, it's the cosmic speed limit, the boundary beyond which cause and effect break down. Nothing can outrun light because light defines the structure of reality. It is the metronome of the universe, the reference pace against which time itself flows. To change c is to tug at the threads of spacetime, rewiring causality and rewriting every physical law built on relativity. No wonder scientists defended the idea so fiercely. It wasn't just about light, it was about everything. But Einstein, brilliant as he was, did not have the final word. As physics expanded, cracks slowly appeared at the edges of this shining framework. Quantum mechanics arrived with uncertainty, probability waves, particles that behaved like ghosts, and suddenly, space-time felt too rigid, too clean. Relativity governs the very large: planets, black holes, galaxies. Quantum theory rules the very small: electrons, quarks, photons. Each works perfectly in its own domain, yet the two refuse to merge peacefully into a single theory. And at that intersection, where the universe is both vast and tiny, lies quantum gravity, the looming unknown. Some of its theories whisper a dangerous possibility. The speed of light may not be as constant as Einstein believed. Maybe c changes with energy, maybe with direction, maybe across cosmic time. If so, the constant that shaped relativity could wobble. Not everywhere, but subtly, maybe only in extreme situations. So here we stand, atop Einstein's century-old revelation, looking down into theories that twist space-time into foamy quantum threads. Relativity made c sacred, but new physics suggests that even sacred rules might bend. And that leads to the next question, the next escalation, the next chapter in this accelerating story. If the universe challenges constant CE at the smallest scales, what does that mean for the very foundations of physics? Einstein unified space and time, but quantum mechanics shattered certainty itself. And between them lies the deepest fracture in modern physics. Relativity paints the cosmos as a smooth fabric, curving under the weight of mass and energy. Quantum theory, on the other hand, sees reality as jittery and granular, built from particles that flicker in and out of existence like sparks in a cosmic storm. One theory describes planets and black holes, the other governs atoms and the subatomic chaos beneath them. Both are astonishingly accurate, yet when we try to stitch them together, the mathematics rips apart. And hidden in that rip is a question more dangerous than it first appears. What if the speed of light isn't truly constant on every scale? At the heart of relativity lies Lorentz invariance, the idea that the laws of physics look the same no matter how fast you're moving, no matter which direction you're traveling. It is what guarantees that c remains fixed, that time dilates predictably, that space-time behaves like a single consistent framework. But quantum gravity theories, especially those exploring Planck-scale physics, hint that Lorentz invariance may not be absolute. If space-time isn't smooth but foamy, turbulent, granular, on unimaginably tiny scales, then light might scatter differently depending on its energy. High-energy photons could interact with space-time differently than low-energy ones, arriving just slightly earlier or later after crossing billions of light years. And if that happens, then the constant we call c might not be one number, but a spectrum. A value that shifts subtly depending on the quantum structure beneath reality. This is where trouble becomes possibility. If quantum gravity allows c to vary, even by trillionths of a percent, then hidden fingerprints of that variation should already be woven into cosmic light. Every gamma ray burst, every pulse from a distant magnetar, every flash from a quasar traveling through ancient space might carry evidence of spacetime at its most fundamental, chaotic level. But the challenge is colossal. We're not talking about human-scale experiments. We're talking about using the universe itself, billions of light years across, as a laboratory to test the limits of Einstein's sacred constant. And that brings us to the next leap. If the very fabric of space-time may distort the speed of light, then perhaps distant stars and exploding galaxies are already revealing it. So how do we listen to them? How do we turn the cosmos into an experiment precise enough to catch a photon arriving late by trillionths of a second? If quantum gravity whispers that space-time may have texture, a grain, a shimmer, a hidden turbulence, then we can't probe it with a lab bench and a laser. The scales are too small, the energies too vast. But the universe itself is built on those extremes. Instead of trying to simulate the cosmos, scientists realized we can use it. Distant stars become beacons. Exploding galaxies become clocks. Every photon fired across the cosmos is an experiment already in progress, and for billions of years, those photons have been racing toward us like marathon runners from the edge of time. If the speed of light varies even slightly, those photons won't cross the finish line together. Gamma ray bursts, some of the brightest, most violent events in the universe, release photons across a spectrum of energies. Pulsars, rapidly spinning neutron stars, flash like cosmic lighthouses with perfect regularity, each pulse a tick of nature's clock. And active galaxies, fueled by supermassive black holes, spew jets of high-energy radiation millions of light-years long. These aren't gentle signals. They're extreme, intense, chaotic. And that chaos is exactly what we need. Because high-energy photons should be the first to reveal cracks in constant C. If space-time bends differently for more energetic light, then gamma photons should lag behind or surge ahead, compared to their lower energy siblings. The greater the distance, the more noticeable the drift. This phenomenon, photon dispersion, is the key. If the speed of light depends on energy, then photons born at the same moment could arrive separated by seconds, milliseconds, even microseconds after a cosmic journey spanning billions of years. A tiny fluctuation amplified by unimaginable distance becomes measurable. In other words, the farther the light travels, the louder the universe speaks. So telescopes watch for bursts, sharp signals, bright spikes, sudden flares where thousands of photons depart together in an instant. If nature runs like Einstein promised, they should arrive like soldiers marching in sync. But if quantum gravity has a say, the formation might break. And now we reach the next phase. Not theory, but observation. We've built detectors that stare at the heavens for years, collecting stories written in starlight, decades of gamma ray data, pulsar timing archives, bursts recorded, catalogued, compared. Somewhere inside that mountain of measurements, a pattern could be waiting. Faint, fragile, but transformative. The only question is, have we gathered enough light, enough distance, enough time to hear the universe whisper? Collecting cosmic light isn't like gathering samples in a neatly labeled laboratory drawer. Every gamma-ray telescope has its own personality, its own detectors, its own blind spots, its own way of translating raw photons into data. One instrument sees sharp peaks where another sees noise. One captures high-energy bursts beautifully but struggles with timing, while another timestamps perfectly but loses sensitivity at the extremes. And the universe doesn't wait for us to standardize our tools. It erupts when it wants, where it wants, in energies we often aren't ready for. So, for decades, astronomers had fragments. Bursts observed in 1997 with early gamma-ray monitors, bursts recorded in the 2000s with Fermi, bursts captured recently with instruments far more precise. The story was scattered, inconsistent, hard to compare, like trying to solve a puzzle where every piece is cut by a different manufacturer. This is where the new study took on a monumental task. Instead of cherry-picking data or relying on one observatory, the researchers dug into the archives, decades worth of gamma-ray bursts, pulsar emissions, and high-energy cosmic flashes. They recalibrated old datasets, correcting for biases and uneven sensitivity. They updated timing uncertainties, revisited energy distribution estimates, and built a framework where data from different eras could finally speak the same language. The process was slow, meticulous, and unforgiving. Small errors in energy calibration could mimic a variation in light speed, so every number had to be checked, every timestamp re-evaluated. This wasn't just analysis, it was excavation. The greatest challenge wasn't scarcity, it was diversity. Observations from space-based telescopes like Fermi or Swift had to be reconciled with older ground-based arrays, each affected by atmospheric interference, software limitations, and technological evolution. Systematic uncertainties, those subtle biases baked into instruments, had to be accounted for. An early detector might consistently overestimate energy at the high end, creating a false signal of dispersion. A later telescope might clip extreme photons entirely. Without unifying factors, one could build an argument for variable C simply by stacking mismatched measurements and mistaking instrumental quirks for cosmic truth. But the new research didn't let that happen. It built a single dataset, carefully harmonized, statistically cross-checked, corrected where needed, and flagged where unknowns remained. When they were finished, they weren't looking at scattered observations anymore. They were holding a map of light across time, across energy, across the sky. For the first time, the cosmos could be treated as a single experiment, rather than a collage of disjoint signals. And with that dataset, the door finally opened to push Einstein's constant harder than ever before. The only question now, with decades of gamma-ray photons aligned, calibrated, and compared, is what story the universe told when everything finally lined up. Imagine you have 60+ cosmic explosions, each recorded by different telescopes, at different energies, from different corners of the universe. It's like trying to compare the sound of thunder recorded on phones, vintage tape recorders, and cutting-edge studio mics. You might find patterns, but unless you translate everything into one compatible format, you're just comparing noise to noise. Physicists needed a universal language, something that would allow gamma-ray bursts, pulsars, and active galactic nuclei to be treated as pieces of the same experiment. Raw timing delays alone couldn't do it. Instrument calibration alone couldn't do it. They needed a framework capable of expressing deviations in the speed of light in a way every dataset could contribute to. And so, they reached for a powerful theoretical dictionary, the Standard Model Extension. The SME is a kind of master blueprint, a theoretical framework designed to capture any possible violation of Lorentz invariance, even tiny ones far below the threshold of ordinary measurements. Instead of assuming that C must be identical everywhere, the SME allows physicists to mathematically describe what it would look like if light traveled slightly differently depending on direction, energy, or interaction with the structure of spacetime. It takes countless messy observational differences, detector sensitivity, photon energy, cosmic distance, and filters them down into a small number of measurable coefficients. These numbers are like dials. If they're zero, Einstein's universe stands unbroken. If even one of them drifts, the door to new physics flies open. But here's the clever part. Instead of analyzing polarization-dependent effects, which get messy fast, the researchers focused on non-birefringent coefficients, the cleaner signals, where photon polarization doesn't complicate interpretation. These specific parameters are directly tied to photon dispersion, the phenomenon where high-energy light might travel at slightly different speeds than low-energy light. By reducing every photon arrival pattern into SME dispersion coefficients, the team did something no one had successfully done before. They converted decades of scattered cosmic data into a unified set of variables, solvable across the entire sky. 65 measurements, 25 coefficients, a universe-sized equation finally simplified enough to test. Now, with all observations speaking the same mathematical language, they could ask a precise question. Do the SME coefficients reveal a crack in constant C, or do they collapse back to zero, reinforcing Einstein's rulebook? The answer would not come from one telescope or one burst, but from the collective voice of the cosmos itself. So, with this new translation, this rewiring of data into a single system, scientists could finally tighten the net around light's speed like never before. But once they solved those coefficients, what did they see? 1 gamma-ray burst might hint, 10 might whisper, but 65? That begins to sound like the universe clearing its throat. A single cosmic explosion could easily mislead. Its photons could be scattered, delayed inside the blast itself, distorted by magnetic fields, or corrupted by the quirks of a telescope detector. Even the most perfect burst is noisy in isolation. But when scientists collect dozens of independent bursts, pulsars, and active galactic nuclei, they're no longer looking at individual anomalies. They're listening for a pattern that repeats across the sky. No single observation can challenge Einstein. But 65 coordinated measurements? Now the cosmos starts speaking statistically, not emotionally. Each measurement was translated into the SME framework, not as a yes/no signal, but as a probability, a range of values describing how likely each burst was to support or contradict constant C. Instead of looking for one huge red flag, researchers looked for clusters, correlations, subtle directional biases, or consistent offsets between high energy and low energy arrival times. Think of it like mapping mountain peaks in a foggy landscape. One peak might be a mirage, but if 20 peaks line up in the same direction, the fog becomes less mysterious. By solving for 25 coefficients simultaneously, they mapped how light speed variations, if real, might depend on direction or energy. A sky-wide diagnostic grid stretching across cosmic history. This matters because uncertainty shrinks when data multiplies. 2 bursts reduce noise slightly. 10 do it more. 65 compress the wiggle room like hands tightening around a knot, squeezing possibilities into smaller and smaller corners of parameter space. If any coefficient tried to escape zero, even slightly, the combined probability field would flare, revealing a deviation too consistent to ignore. But if nothing flares, if every dimension stays quiet, then Einstein's constant holds, at least within the limits of our cosmic reach. And that's what makes this moment so crucial. Not just volume, but diversity. Different energies, different redshifts, different sky directions. A universe-spanning testbed, finally dense enough to make precision meaningful. Still, even such a vast dataset cannot close the book entirely. It narrows the room in which new physics could hide, dramatically, but does not eliminate the possibility. we are no longer looking for a wild, roaring break in constant C. We are listening for the faintest tremor, the smallest slippage. And now, with this map complete, the question sharpens like a blade. Did the coefficients bend? Did any dimension show the slightest rebellion against constant light speed? So here's the moment of truth, the kind every physicist feels in their chest, like a drumbeat. After harmonizing old data, translating it through the standard model extension, solving for 25 parameters with 65 independent cosmic sources, the final question became inescapable. Did light's speed actually vary? And the answer, as often happens in science, was subtle. Not a triumphant discovery, not a collapse of Einstein's legacy, but something beautifully frustrating. No clear variation was detected. No coefficient broke free from zero with confidence. Instead, the study tightened the allowable range of deviation by around an order of magnitude, meaning if C does vary, it hides within a range 10 times smaller than previous experiments could even see. This is not disappointment, it's precision. No detection does not mean no variation exists. It means that if variation is real, it must be faint, delicate, tucked beneath thresholds current instruments can barely touch. Imagine listening for a whisper in a hurricane. You hear only wind, but that doesn't prove silence. It merely defines how soft the whisper must be. In physics, this is what setting limits means. Researchers don't prove that C is permanent. They prove how close to permanent it must be. Every constraint is a narrowing cage, squeezing hypothetical variation into smaller and smaller corners of possibility. A decade ago, variation could have been relatively large. Today, it must be microscopic, almost ghost-like. Tomorrow, even that might shrink. And this is why the result matters more than it first appears. Tighter bounds reshape the frontier. They inform future theory. Quantum gravity models predicting dramatic breakdowns of Lorentz invariants now find their parameter space severely restricted. If spacetime foam slows high-energy photons, it does so by an amount too tiny for our best detectors to isolate, so far. But technology grows claws. New telescopes sharpen vision. Gamma-ray detectors now monitor the sky with faster timing and higher energy reach than ever before. Space observatories launch with precision clocks capable of tracking photon arrival times to millionths of a second. A single next-generation trigger, a hyper-energetic burst, a closer magnetar flare, a cleaner signal, could reveal what this study only brushed against. Einstein's constant emerges not triumphant, but undefeated, still standing, still unbroken, yet now tested more severely than at any point in human history. This isn't the end of the story. It's the tightening of a screw, the sharpening of a question, the calm before a louder experiment arrives. Because if variation hides at extreme energies or distant redshifts, this analysis might be only the threshold, the doorway into stranger physics. So the next question becomes irresistible. If C holds strong here, where else might we look for it to falter? Extreme conditions, earlier cosmic epochs, higher photon energies, the edges of reality itself. Why worry if the speed of light shifts by trillionths of a percent? You don't feel it when you switch on a lamp. Your phone doesn't glitch. The sun still rises. But beneath everyday reality lies a universe held together by equations. And C is the keystone that keeps the arch from collapsing. It sets the structure of spacetime, dictates how cause leads to effect, governs how particles move and how energy transforms. If that keystone wobbles, even slightly, Every beam of modern physics bends with it. Relativity depends on it. Maxwell's equations depend on it. GPS satellites literally correct for relativistic effects involving CE every moment you navigate. A. Variable speed of light wouldn't just tweak a formula. It could reshape the very geometry of reality. Imagine a universe where C depends on photon energy. High-energy light might outrun low-energy light, rearranging what we mean by before and after across cosmic distances. Causality, the idea that causes produce measurable effects in order, could warp in strange ways. Two events we see as simultaneous might not be. The cosmic speed limit might not be universal. If C varies over time, then the early universe may have unfolded differently than we think. Maybe faster expansion didn't require dark energy in the same form. Or ideas like cosmic inflation could be replaced by something more radical. Suddenly, the Big Bang timeline might stretch or compress. The observable universe might not be bounded the way we assume. Even a tiny deviation in C today could imply huge differences billions of years ago. This is where theories like quantum gravity and early universe cosmology step in. They propose spacetime isn't smooth. It might flicker and fluctuate at the Planck scale, turning light speed into a locally shifting property rather than an eternal constant. Or maybe, in the infant universe, C was much higher, allowing distant regions to equalize temperature without requiring inflation. These aren't fringe fantasies. They're serious attempts to solve long-standing cosmological puzzles that relativity alone struggles with. A varying C could rewrite our understanding of the horizon problem, structure formation, even the origin of quantum fields. And yet, the universe has been stubbornly quiet, giving us no clear break, only ever tighter limits. But silence isn't certainty, it's potential. The possibility alone forces us to reconsider how deeply we trust our constants. What if C is only apparently constant under the conditions we can measure, but flexible under the ones we haven't reached? What if the universe holds its secrets in regimes just beyond our instrument's grasp? To see where this leads, we turn next to the boldest proposals. Theories built not on the assumption that C is constant, but on the suspicion that it might not be. The idea that light's speed might not always have been constant didn't begin in some fringe forum. It erupted inside mainstream cosmology less than 3 decades ago. Early 2000s theoretical physicists, including João Magejo and Andreas Albrecht, dared to propose something almost sacrilegious to Einstein. What if C was much higher in the early universe? At first glance, it sounds wild, but it was meant to solve very real cosmological puzzles. Why do regions of the universe, billions of light years apart, share the same temperature if they should never have been in causal contact? Why is space so flat, so uniform, so ordered? Standard cosmology answers with inflation, a brief, exponential expansion that smoothed everything out. But inflation is complicated, reliant on hypothetical energy fields we've never observed directly. VSL offered a simpler alternative. If light once moved faster, information could have spread more easily, equalizing the cosmos without invoking an inflationary mechanism. VSL theories suggested that in the extreme heat and density of the Big Bang, C may have been dynamic, high enough to allow distant regions to exchange light and energy freely. As the universe cooled, C would settle, freezing into the near-constant value we measure today. No exotic inflaton fields, no fine-tuned expansion, just a changing speed limit in the first cosmic moments. Elegant? In some ways, yes. Revolutionary? Absolutely. And also deeply controversial. Accepting VSL meant discarding one of relativity's sacred pillars. causality, spacetime geometry, fundamental symmetry, all would need reformulating. These ideas didn't just expand physics, they threatened to reroute it entirely. And that is why VSL drew so much attention. It challenged the default assumption that constants are forever, opening the door to a universe where laws evolve rather than merely exist. But elegance doesn't equal truth. A theory lives or dies not by beauty, but by evidence. And so, after the shock of its proposal, the scientific world turned toward the next necessary question, one that would decide whether VSL was revolutionary insight or mathematical mirage. Could we test it? Could observations confirm or refute a universe where C once ran wild? A theory becomes science only when it risks being wrong. VSL wasn't just a clever idea, it offered testable consequences, hints that might still be written across the universe like ink that never dried. If light once travelled faster, then the early universe should bear scars of that freedom. Temperature should have equalized smoothly across the sky, structures should have formed with different timing, and the cosmic microwave background, the oldest light we can observe, should carry signatures of that altered physics. Not chaos, but subtle distortions, ripples, alignments, or spectral features inflation doesn't predict. If inflation is a flash flood, VSL is a fast river upstream, and its flow would leave marks. The CMB became the critical battlefield. It is a snapshot of the universe 380,000 years after the Big Bang, a photograph of cosmic infancy. Tiny fluctuations in temperature across that ancient glow reflect density variations that later grew into galaxies, clusters, and cosmic webs. Inflation predicts a very specific pattern in that map, one we've measured with exquisite precision using satellites like WMAP and Planck. But a universe with a varying speed of light might produce a different pattern. Slightly altered correlations between hot and cold regions, shifts in the acoustic peaks, or an unusual degree of uniformity without needing inflation's explosive expansion. If C once stretched space's causal reach, the horizon problem dissolves naturally, and the CMB should reflect that simplicity. Cosmologists didn't let VSL rest untested. They ran simulations, adjusted early universe equations, and compared predictions against the CMB's delicate grain. They analyzed matter distribution, studied baryon acoustic oscillations, examined how galaxies assembled over time. They searched for discrepancies inflation couldn't explain, but VSL could. Some results hinted compatibility, others fell short. No smoking gun emerged, but neither did VSL collapse under scrutiny. The theory survived, constrained but not destroyed. It became a shadow possibility, not dominant but not dismissed, waiting for higher precision or cleaner cosmic signals. And that brings us back from early epochs to the data flooding in today. Gamma-ray bursts, quasars, supernovae, high-energy photons racing across billions of years. CMB tests probe the past. Current observations test the journey. The stakes are enormous. If a deviation shows consistently in both ancient and modern light, VSL wouldn't just be plausible. It could be the bridge between cosmology and quantum gravity. So we now turn to what the universe told us next. When cosmologists confronted VSL with observational limits strong enough to sharpen or shatter it. If varying C theories once stood like bright sparks of rebellion, observational cosmology became the cold, steady wind, testing whether any spark could catch. The universe itself had to answer. Did light ever run faster, slower, differently than it does now? To find out, scientists didn't look to one signal, they looked to many. They gathered Type Ia supernovae as cosmic mile markers. They mapped baryon acoustic oscillations, the frozen echoes of ancient sound waves rippling through early plasma. They measured the cosmic microwave background with exquisite fidelity. These are the fingerprints of the universe's expansion history, and if C changed noticeably, even briefly, its effects would ripple into these structures like tension marks on cooling glass. Supernovae provide a cosmic distance ladder. If C varied, luminosity distances at different redshifts wouldn't line up with expectations from standard cosmology. Baryon acoustic oscillations, the large-scale clustering of galaxies, encode how sound traveled through the early cosmos. If light once moved faster, sound horizons would shift, changing the spacing of galaxies even billions of years later. And the CMB, the universe's own baby photo, would broadcast the consequences across the entire sky. Peak ratios would warp. Temperature fluctuations might equalize too efficiently or not enough. Patterns would drift from the inflation-predicted curve. When cosmologists compared VSL predictions against these datasets, the result was striking. Not a rejection, but a tightening. The room in which variation could hide shrank dramatically. One particular analysis in 2014 applied CMB data, supernova observations, and BAO measurements together, and found that any possible change in C was extremely small, less than around 1%, perhaps as low as 0.01 or below. Not zero, but small enough that if variation exists, it must operate gently, subtly, either in early epochs or only under extreme conditions. This is what tight constraints mean. They don't kill a hypothesis. They corner it. They say, if light ever changed speed, it did so under parameters you must now obey. Theories predicting dramatic shifts lost ground. More nuanced, energy-dependent versions had room to survive. VSL didn't vanish. It became a quieter possibility. But here's the twist that keeps the debate alive. Every constraint depends on assumptions. Did the early universe evolve exactly as lambda CDM predicts? Are supernovae perfect standard candles? Are BAO structures interpreted without hidden biases? Even the CMB, our most precise cosmological map, requires models to decode. If those models shift, even slightly, allowed variation in C could reopen like a curtain. And data is far from uniform. Most tight constraints apply to low and mid-redshift observations, the recent universe, not the deep past. Farther back, uncertainty widens. Earlier epochs remain foggy. If C differed dramatically in the first milliseconds of cosmic history, current observations might only reveal the afterglow, not the act. This leaves us in a tantalizing middle ground. Variation is not confirmed, but neither is it ruled out absolutely. We have limits, not final answers. Every new telescope, every deeper supernova survey, every improved BAO map pushes those limits tighter or exposes overlooked cracks. A universe with constant CE still looks most consistent with the data, but the possibility remains like a faint outline no one can fully erase. And now, attention turns to the frontier beyond supernovae and BAOS, to measurements reaching deeper into time and higher in photon energy. Because if variation hides beyond redshift 2, if it manifests only in extreme cosmic moments, then we must look farther, harder, deeper into the dark. Redshift is our time machine. The farther away a galaxy or quasar is, the longer its light has been traveling, and the more its wavelength has been stretched by the expanding universe. A redshift of 0.1 means the light has been en route for roughly 1 billion years. A redshift of 2 means we're seeing the universe as it was more than 10 billion years ago, young, dense, hot, chaotic. If light ever ran differently, faster, slower, or energy dependent, then high redshift signals are where we should look. Lower redshift observations paint a calm, stable picture of C, but farther back the cosmos was raw and unfamiliar. Physics may have behaved differently then. The question is, does the universe's distant light reveal that difference? In 2023, researchers pushed deeper into cosmic history by scaling beyond standard supernova surveys. Type Ia supernovae are bright explosions that act as standard candles, letting us estimate cosmic distances by comparing how bright they appear to how bright we know they should be. But beyond a certain distance, supernovae become too faint to rely on alone, so scientists turned to quasars, the hyperluminous cores of galaxies powered by supermassive black holes. Quasars shine bright enough to be visible billions of light-years away, allowing us to extend the cosmic ruler farther than ever. Using updated Hubble diagrams, the relationship between redshift and luminosity distance. The study compared what distances should look like if C were constant versus what they'd look like if C varied. The result? No strong evidence for variation, at least up to redshift approximately 2. But this finding was wrapped in nuance. The uncertainties grow with distance. Quasars, unlike supernovae, are not perfectly standardizable sources. Their luminosity depends on complex accretion physics that still challenges astrophysical modeling. Even so, the data didn't demand a change in C, it simply didn't prove one either. If variation exists beyond redshift 2, we may not yet have looked far enough. And if variation is energy dependent rather than time dependent, luminosity distance tests may be blind to it entirely. It's like searching for fingerprints with the wrong kind of light. The evidence may be there, but invisible to the instrument. No strong evidence is not a full stop, it's a comma, a pause, a tightening of the possible rather than an erasure of the unknown. Because while supernovae and quasars push our reach, across time, they don't stretch across energy. And if C varies with photon energy, we need a different kind of messenger. Something sharper, hotter, faster, something born in cosmic violence and hurled across the universe with enough force that even the smallest delay could accumulate like compound interest. That is where gamma-ray bursts enter the story, the brightest explosions known, the most energetic photons nature produces, stitching together the story of CE not by distance alone, but by energy over distance. If variation hides anywhere, it may be here, in the blinding edge of physics. The 2025 analysis didn't shatter Einstein's cosmic speed limit, it squeezed it. Hard. By combining gamma-ray bursts across eras, harmonizing detector uncertainties, and translating everything into SME coefficients, researchers carved away huge swaths of theoretical space where variation could have lived. What used to be plausible is now almost impossible. Parameter ranges once wide enough to drive a theory through have collapsed by an order of magnitude, meaning the allowed wiggle room for C variation is now roughly 10 times smaller than what previous studies allowed. If the universe ever lets light travel unevenly, it does so far below the scale our instruments have been able to detect. So far. This is where language matters. A limit is not a dismissal. No smoking gun isn't the same as no weapon exists. What the study achieved is more like tightening a net, pulling the mesh closer until almost nothing passes through, but still leaving microscopic gaps. Photons from GRB 221009A and dozens of other bursts didn't show dispersion, but absence of evidence is not evidence of absence. The photons we detected may not have been energetic enough. The bursts we've seen may not be distant enough. The effects, if real, may only appear under conditions we have yet to witness, near black hole horizons, inside early cosmic epochs, or at energies beyond today's detectors. Still, the results reshape the landscape. Theories predicting large Lorentz violations now face extinction. Quantum gravity models with bold light speed shifts must shrink, adapt, or die. What remains viable are subtler possibilities, variation confined to Planck-scale energies, or only emerging at redshifts far beyond 2, or manifesting directionally rather than universally. The 2025 dataset didn't close the book. It sharpened the next chapter. It told theorists, if C varies, your path is narrow. Find it if you can. And that's why this breakthrough is thrilling instead of disappointing. Science advances not only through discoveries, but through constraint, through eliminating worlds that aren't, leaving only those that might be. As detectors evolve, limits will tighten again. Future observatories will capture photons with finer timing, greater energy range, and wider sky coverage. The whisper of variation, if it exists, might yet rise toward audibility. But until then, we walk in a universe where C stands strong, unbeaten, but not unchallengeable. Which leads to a deeper question. If we cannot yet prove C varies, why is proving it so hard? What stops us from ruling it out completely? If constant C is the backbone of physics, why can't we simply prove it and move on? Because proving a universal negative, that light never, anywhere, under any condition, at any time in the universe's 13.8 billion year history, has ever traveled differently, is not an experiment. It's an impossibility. You could measure billions of photons flawlessly and still never know whether one, somewhere, slipped through reality differently. Science can only shrink the space where variation could hide, never eradicate it entirely, and so our instruments chase a phantom, not proof of constancy, but the last remaining shadows where inconsistency might lurk. Our technology, remarkable as it is, still carries limits like scars. Detectors have thresholds. They miss faint ultra-high energy photons. Timing resolution, even when measured in microseconds, may still be too coarse to catch a dispersion delay built from Planck scale differences stretched across cosmic time. Calibration drifts. Clocks misalign by nanoseconds. Comparing bursts across instruments sometimes means comparing eras, with software updates and hardware rewrites in between. Every step introduces uncertainty, and any uncertainty could mimic, or conceal, a true variation in C. Even the most precise photon arrival times might reflect the telescope more than the cosmos. And then there's the source itself. A gamma-ray burst doesn't fire photons like bullets from a synchronized barrel. It is chaos, jets forming, collapsing, magnetic fields twisting, shock waves colliding. High-energy photons might be emitted milliseconds later than low-energy ones simply because the explosion's engine staggered. If a delay arrives on Earth, is it because quantum gravity bent reality, or because a black hole coughed? We rely on astrophysical models to untangle emission timing, but every model is a guess, and every guess can blur the line between cosmic physics and source behavior. The problem compounds further. Light doesn't cross the universe unscathed. Along the way, it may interact with cosmic dust, background radiation, gravitational lenses. Tiny environmental effects, even if negligible, can stack into confusion. To detect variation at levels we're now testing, we need not just photons. but certainty about everything that happened to them from birth to arrival. Right now, certainty is the rarest element we have. This is why proving the constancy of C is harder than disproving it. A single clear deviation would rewrite physics overnight, but billions of consistent arrivals prove only that variation has evaded us so far. The door remains cracked, not wide, but unsealed. To close it further, we need new detectors, faster clocks, broader skies, instruments capable of hearing the universe in higher definition. So the next step is obvious and inevitable. If today's telescopes bring us close, what kind of technology would finally push us beyond uncertainty, into the realm where even whispers of variation must reveal themselves? If the universe is hiding tiny fluctuations in the speed of light, then our instruments must evolve from ears that hear thunder to ears that hear whispers across galaxies. The next generation of observatories is already on the horizon, machines built not just to see light, but to question it. New gamma-ray telescopes will watch the sky continuously, with timing precision fine enough to capture photon arrivals separated by microseconds or even nanoseconds. Space-based detectors free from atmospheric distortion will register higher energy photons than any instrument before them. And as these telescopes widen their sensitivity, bursts once too faint or too fast to analyze will come into view like lightning strikes that were always there but never noticed. Upcoming missions like Imago X and CTA, built for extreme energy photon astronomy, could detect gamma rays 10 times more energetic than current tools, probing dispersion signatures that today hide below noise. Meanwhile, wide-sky monitoring networks will ensure that no cosmic explosion slips by unrecorded. We move from occasional data points to a continuous stream, from astronomy as hunting to astronomy as listening. Standard candle surveys will push past redshift 2 into epochs where early universe variation, if real, may finally reveal itself. And gravitational wave observatories, already capturing ripples in spacetime, offer a new axis of comparison. If light and gravity propagate differently across cosmic distances, the timing mismatch itself becomes evidence. Multi-messenger astronomy, light plus gravity plus neutrinos, turns the universe into a triangulated lab. Yet the most radical step may come from quantum technology. Experiments like quantum correlated photon timing could measure differences as small as 1 part in 10 to the 22nd power. Laboratory tests at the Planck scale, once science fiction, are crawling toward reality. Cosmological surveys like Euclid and the Vera-Rubin Observatory will map structure, voids, and cosmic expansion with unprecedented granularity. Every galaxy becomes a data point. Every quasar, a clock. Every burst, a test of Lorentz symmetry. The future isn't just more data, it's better data. Cleaner signals, higher energy, deeper history. Instruments designed not to assume constant C, but to challenge it deliberately. If light has ever wavered, these machines will catch it. And if they don't, if the universe remains silent, then the speed of light stands taller than ever, validated not by one experiment, but by an era of precision cosmology. The question is no longer, can we test it? It's, how much further can we push the boundary before nature finally answers us? If the speed of light is not a universal constant, then we are not standing on bedrock. We are standing on a raft floating in deeper waters than we ever imagined. A wobbling sea would not just alter one equation, it would ripple through physics like a tectonic shift, touching everything from causality to quantum gravity. Relativity's foundation, that the speed of light is the same for all observers, would suddenly become conditional rather than absolute. Clocks in relative motion might disagree not just by relativistic correction, but by deeper, energy-dependent distortions. Two events that seem simultaneous to one observer could diverge in ordering for another, not because of motion alone, but because the very speed of information exchange differed. Cause and effect, the skeleton of reality, could flex. Think about that for a moment. If light speed fluctuates, the boundary between what can influence what might shrink or stretch dynamically. Horizons, cosmic speed limits on information, could move. Black hole event boundaries, normally one-way membranes, might behave differently for different energies. Imagine a universe where certain particles outrun low-energy photons, racing ahead into regions light cannot yet enter. Temporal sequences might strain. Did event A cause event B, or did B happen fast enough to influence A retroactively in another frame? Even tiny deviations in C could accumulate into dramatic consequences over cosmic distances and energies. And then there's cosmology, the story of how everything began. If C was higher during the Big Bang, the early universe could have mixed, thermalized, and equalized without the need for inflation. Galaxies might have formed differently. Structures might have unfolded without the sharp push inflation provides. A faster C early epoch could relax several cosmological tensions in one stroke. The horizon problem, the smoothness of the CMB, the early formation of massive structures. The equation of state for radiation-dominated epochs could shift. Expansion histories might need rewriting, not subtly, but fundamentally. Lambda CDM, our standard cosmic model, could transform into something stranger but more self-contained, no longer needing stretches of super-light expansion to stitch the universe together. Most profound of all, quantum gravity, the century-long missing link between general relativity and quantum mechanics, could reorganize around variable CE like iron filings around a magnet. Many theorists suspect that light speed invariance may break down at Planck scales, where space-time becomes foamy and granular. If we one day measure a variation in C, that becomes a compass arrow pointing toward the right model of quantum gravity. It could favor loop quantum gravity over string theory, or vice versa. It might imply space-time emerges from deeper quantum information networks, not as a background, but as a phase of matter-like geometry. A variable C could reveal that space-time isn't eternal. It's dynamic, evolving, even flowing like a medium with properties that change across energy or era. Yet, and this is where caution must hold hands with imagination, rewriting the universe requires more than anomalies and maybes. You don't dismantle relativity with hints. You don't replace inflation with poetic possibility. Physics moves only when evidence stacks, independent, repeatable, undeniable. A universe with variable C would change everything, which is exactly why the threshold for believing it is so high. So before textbooks are rewritten, before models are replaced, before space and time are reinterpreted at their roots, science needs more clarity, more signals, more sky. And that brings us to the next challenge. If questioning constant C carries enormous theoretical promise, why do many physicists still resist it with such force? For over a century, C hasn't just been a number. It has been the backbone of theoretical physics, the constant on which the very structure of spacetime hangs. Changing it would be like pulling one stone out of an arch and hoping the entire bridge doesn't collapse. That's why, even with provocative hints and theoretical models suggesting variation, the overwhelming majority of physicists still treat C as sacred. Not because they refuse to imagine alternatives, but because too much depends on that one constant remaining fixed. Quantum field theory assumes Lorentz invariance. Electromagnetic waves propagate because Maxwell's equations hold their symmetry, tied directly to CA. GPS works because C remains stable enough for relativity to correct satellite timing. Alter C, and every one of those equations must be rederived from the ground up. The ripple effects would be enormous. Changing C doesn't mean adjusting one parameter. It means rethinking causality, energy-momentum relations, particle interactions, cosmological equations, event horizons, vacuum fluctuations. The Standard Model, which describes every known particle interaction except gravity, would need revisions wherever C appears, explicitly or implicitly. General relativity would need to redefine how curvature interacts with light cones and how spacetime evolution unfolds. For many physicists, modifying such a cornerstone without overwhelming evidence feels like breaking open a cathedral to inspect whether one stone is loose. Until a crack splits the structure. Why risk destabilizing what works? There's another reason for caution. VSL theories are diverse, sometimes wildly so. Some propose seed changed only in the early universe. Others claim it varies with energy or direction. Others suggest step-like shifts across cosmic epochs. Without a unified mechanism or consensus model, VSL can appear speculative, a family of ideas instead of a coherent theory. And speculation, even elegant speculation, cannot outweigh the success of a framework that predicts everything from gravitational waves to particle accelerators with stunning accuracy. As long as constant C continues to match observation with high precision, the burden of proof lies with the alternative. That doesn't make resistance a flaw. It makes it part of science's immune system. Paradigms don't fall because they are challenged. They fall because evidence overwhelms them. History shows this pattern again and again. Newton stood until Einstein replaced him. But only after Mercury's orbit, time dilation experiments, and the bending of starlight said Newton isn't enough. Evolution replaced classical thermodynamics in biology only after fossils, genetics, and molecular inheritance converged like floodwaters. Science doesn't move because someone dreams. It moves because reality forces its hand. And that's the real tension. Theories questioning C are exciting. They offer new solutions, new physics, even pathways to quantum gravity. But without rock-solid observational backing, most researchers hold position, steady as granite. They wait for the evidence that doesn't just hint, but demands a new framework. Because once the wall cracks, everything must be rebuilt. So the question becomes, has the new study, the most rigorous test to date, changed the balance? Does it mark a turning point, or simply another constraint? To answer that, we must look at why this study stands apart from everything before it. What makes the 2025 analysis stand apart, the reason it's already being described as a milestone, is that it didn't just add one more measurement to an existing pile. It rebuilt the pile from the ground up. Earlier attempts to test whether C varies often relied on isolated gamma-ray bursts, fixed detector sets, or inconsistent calibration methods. One study might see a hint of delay and claim new physics. Another might see none and conclude constancy. The result was a scientific stalemate. Data everywhere, agreement nowhere. Every finding could be dismissed as an instrumental quirk, a statistical fluke, or the messy timing of the burst itself. The debate grew, but without coherence, without synthesis. What the 2025 team accomplished was something more ambitious. They gathered decades of light, translated it into one language, and tested it as one experiment instead of many. The novelty is integration. Instead of treating bursts independently, the new study merged 65 independent high-energy events into a single statistical engine. It corrected legacy timing, recalibrated energies, remodeled systematic errors that older studies ignored, and most importantly, translated everything into the Standard Model Extension, SME. This step was revolutionary. SME allowed researchers to express potential Lorentz-violating effects using 25 coefficients across the sky, rather than scattered inconsistencies. Suddenly, decades of chaotic photon arrivals became a multi-dimensional probability space, structured, comparable, solvable. The old noise became a map. In physics, structure is everything. That coherence is why skepticism weakened. When a single burst shows no variation, critics shrug. When 65 bursts agree, statistically, robustly, probabilistically, silence becomes meaning. And the analysis didn't rely on assumptions baked into previous work. It cross-checked instruments across generations, quantified uncertainties instead of hiding them, flagged bursts where astrophysical timing muddies interpretation, and weighted datasets according to reliability. This is what rigor looks like in cosmology. Not just signal, but trust in the signal. Not just numbers, but confidence in the numbers. With this foundation, the study pushed constraints on variable C further than any work before it, an order of magnitude improvement. If C varies, it must hide in territory now 10 times smaller than we previously believed. But this tightening is more than a result. It's a standard. From now on, any claim of variation must surpass this level of precision. No more cherry-picked bursts, no more fragmented datasets. The bar has been raised, and the universe must now answer at higher resolution. But milestones aren't conclusions. They're inflection points. We are no longer asking, can we test the constancy of C? We now ask, how far can we push this test? What remains unprobed? The early universe, extreme energies, Planck-scale foam, lies beyond current reach, inviting a next generation of detectors to take the baton. And so the story advances. If this study set the new frontier, what still stands beyond it? What remains unknown, untested, unexplored at the edges of space-time? The next segment asks exactly that, because every milestone casts a shadow of unanswered questions behind it. Even after the most comprehensive analysis ever attempted, the universe leaves us with a humbling truth. We still don't know everything about light's speed. We know how C behaves here. We know how it behaves across billions of light years in gamma photons we can detect. But the cosmos is bigger than every observation humanity has ever made. Staggeringly, incomprehensibly bigger. Between what we can measure and what remains unseen lies an ocean of uncertainty, deep enough to drown certainty itself. The unanswered questions cluster in the edges, in regimes where current technology cannot reach. What happens near black holes, where gravity crushes space-time into something almost liquid? Do photons near the event horizon move differently, slowed or warped by quantum-level distortions? Could C vary in intense gravitational gradients the way sound speed varies with air density? We've never measured photon propagation at the lip of a singularity. We only infer, and inference is not proof. Then there is the early universe, a domain so hot, so dense, so alien that every law we trust today may have been provisional, temporary, waiting to crystallize into something stable only after the cosmos cooled. If C was ever different, the Big Bang era is the most likely stage. But we cannot observe it directly. We have snapshots, CMB radiation, structure formation, primordial fluctuations, but these are fossils, not live footage. A paleontologist can learn much from bones, but not whether the animal breathed differently while alive. Cosmic background signatures constrain but do not close the case. And energy, the most tantalizing frontier. Our detectors capture high-energy photons measured in giga-electron volts or tera-electron volts. But quantum gravity predicts deviations may only appear near the Planck scale, where energies are 10 to the 15th power times greater. No collider will touch that realm. No current telescope will see it. Variation could exist like a crack in stone, so fine only a diamond-sharp instrument, still hypothetical, could expose it. It may hide only in gamma bursts far beyond GRB 221009A, in events we haven't yet witnessed, in galaxies so distant their light hasn't reached us. Time itself becomes a barrier. Even direction may matter. Lorentz violation could be anisotropic, different in one part of the universe than another. Maybe C is constant here, in our cosmic neighborhood, but shifts subtly elsewhere. Cosmic variance means we sample only one line of sight per burst. 65 isn't the universe. It's a whisper from one slice of it. If spacetime has texture, a foam-like grain, variation might appear only in specific propagation directions. Small enough, today's averaging methods smear it out. We look broadly, but what if variation is narrow and directional, like wind felt only when standing exactly in its path? Instrumental limitations add yet another layer. Timing resolution could still be too coarse. Burst emission physics remains messy. Source uncertainties might hide or mimic real signals. Calibration can drift with temperature, magnetic interference, detector aging. Every experiment walking toward precision walks through fog. We see shapes, silhouettes, but clarity lies beyond the threshold of current instruments. And so the paradox persists. Every test strengthens the case for constant C, yet none can seal it. Constancy might be an emergent feature, a macroscopic illusion built from deeper, variable microphysics. Or it might be the universe's most unbreakable rule. We simply do not know yet. We stand in the space between confidence and curiosity, the most fertile place science ever grows. Which leads to the philosophical heart of this question. If a constant can fluctuate under conditions we can't reach, what does constant really mean? What does it mean for a law to be universal in a universe we cannot fully observe? What does it really mean for a constant to be constant? We say C is fixed, 299,792,458 meters per second. A number etched into physics like scripture. But the universe is not static. It expands, cools, curves, collapses, spawns quantum fluctuations like sparks off a cosmic anvil. We live in a reality where space stretches, time dilates, particles appear and vanish, and vacuum energy bubbles with uncertainty. In such a universe, is constancy even possible? Or is it an approximation, a smooth average over deeper irregularity? Perhaps C is not the iron bar we believe it is, but the frost on a window, clear from afar, but laced with patterns only visible when pressed close. History should make us cautious. Once, the gravitational constant G was assumed unchanging, until theories of scalar tensor gravity proposed otherwise. The fine structure constant, alpha, has been tested for cosmic variation and may show hints of spatial drift in quasar spectra. The proton-to-electron mass ratio, long believed immutable, is now probed across billions of years looking for tiny evolution. Physics is full of quantities once treated as divine, later revealed as contextual. The boiling point of water is constant until you change altitude. The speed of sound is constant until you change density. In emergent systems, constants can emerge too, stable at macroscopic scales even if microscopic rules fluctuate wildly beneath. So what if C is only constant under the conditions we can measure? Constant in cold, sparse space. Constant in the late universe after expansion slows. Constant at energies below quantum gravity thresholds. But near the Big Bang? Near black holes? At Planck energies? If C becomes dynamic there, then constancy is regional, not universal. A rule with a domain, not a decree written across every inch of spacetime. This reframes physics itself. A constant is not just a number, it is a claim about the symmetry of nature. When we assume a value is absolute, we assume the universe treats every place and moment equally. If C varies, that symmetry breaks. Space and time become contextual. The universe may have phases, epochs where laws shift like climates. One early era might have allowed information to flow faster. Another might have slowed photons as structure formed. Our textbooks show one universe. A variable C cosmos would contain many. And perhaps, even if variation is real, we may never experience it directly. It could exist only in realms beyond survival, inside event horizons, in the first microseconds of creation, in particle interactions at energies humanity will never reach. To us, C would remain constant indefinitely, a truth wrapped in accessible reality. We live on the calm surface of a deep ocean. Beneath us, currents may swirl. If the speed of light is constant only here, only now, only within measurable scales, then the universe is stranger and more alive than we imagined. And if laws can change, if constants can evolve, then the cosmos is not a static machine, but a dynamic organism, growing, aging, changing state over billions of years. Which invites the next question. If the meaning of constant is flexible, how does that shape not just physics, but culture? How do ordinary people relate to a universe whose deepest rules may rewrite themselves as our instruments sharpen? We may never feel a variation in the speed of light while crossing the street or sending a text. Yet, the idea that C might not be constant taps into something deeper than measurement. It touches how we define what's real. Constants make the universe feel ordered, dependable, rational. C is a cosmic anchor, one of the few numbers that feels absolute, a foundation that doesn't wobble when everything else does. If that anchor loosens, even slightly, the cosmic map beneath our feet shifts. The everyday world still functions. GPS still syncs satellites to Earth with nanosecond precision. Fiber optic networks still pulse with light at near maximum speed. But the meaning of those systems changes. We realize they work not because C is metaphysically fixed, but because the universe happens to be stable where we are. Relativity didn't change how clocks tick in our kitchens, yet it changed how we think about time forever. It taught us that reality isn't universal. It is relative to motion, gravity, perspective. A varying speed of light could deliver a similar paradigm shift. Imagine waking up to headlines that C runs faster in the early universe or slower near extreme gravity. It wouldn't break your Wi-Fi, but it would break the illusion that nature is simple. It would transform our philosophical vocabulary. Suddenly, constants would look like conditions, temporary agreements written into space-time, not the divine rules we thought they were. Just as quantum mechanics shattered classical certainty, a flexible C could fracture our assumptions about the permanence of cosmic law. Culture has always absorbed physics at its philosophical edges. Einstein introduced time dilation, and soon science fiction asked, what if two lovers age differently across space? Quantum theory birthed teleportation and multiverse scenarios in film. Black holes became metaphors for memory, trauma, infinity. If C varies, storytellers will imagine worlds where communication outruns light, where causality bends, where histories can change direction. Even if real variation remains microscopic, imagination will scale it to myth. Because physics isn't just knowledge, it's narrative. It shapes how humanity tells the story of itself. And even practically, a shift in C would ripple into engineering, computing, cosmology. Models of the early universe would be rewritten. Galactic evolution timelines might shift. Dark energy theories could change shape. Every textbook from grade school to graduate theoretical physics would need revision. A redefined C would become the next relativity moment, a cultural milestone marking humanity's evolving understanding of existence. We live in a world where the unknown drives invention, and when foundational truths evolve, civilization evolves with them. So even if we never feel the wobble of C directly, the search for answers belongs to all of us. It is a test of how much we dare to question, how far we are willing to look beyond the familiar. Because when constants tremble, imagination expands, and the human story deepens. Now, the question turns inward. With everything we've seen, the limits, the hints, the possibilities, how should we interpret current findings? Should we lean toward excitement or caution or both? We stand now at the balanced edge of discovery, halfway between comfort and disruption, between Einstein's certainty and quantum suspicion. The new 2025 analysis doesn't scream revolution, but it doesn't close the case either. It is neither a confirmation that C is eternally fixed, nor evidence that it wiggles beneath our detectors. Instead, it gives us something more subtle and arguably more powerful. A narrower corridor, a sharpened frontier, a measured uncertainty. It tells us where variation is not hiding, and invites us to search more intelligently where it still might be. So, should we be excited? Yes, because tightening limits is progress. Every constraint fences in the unknown, shrinking the jungle where new physics can lurk. We now know that any variation in C, if real, must be extraordinarily small or confined to specific conditions. Extreme energy, deep time, or exotic spacetime regimes. The fact that Einstein's constant survives another trial doesn't make the journey pointless. It makes the universe more precise. Knowledge grows both when we find something new and when we fail to find it. Discovery is not only for eureka, it is also, not here, try deeper. But should we be cautious? Absolutely. This is not the evidence that topples relativity. It is not proof that variable C theories should replace the standard model. We've seen no clear dispersion signature, no directional Lorentz violation, no statistical break from unity. The smartest position is not disbelief, nor blind enthusiasm, but cautious optimism. Enthusiastic curiosity anchored by respect for data. Theories live and die not by imagination alone, but by reproducibility, convergence, and the brutal honesty of measurement. Science rarely leaps, it steps. Newton to Einstein was not a discard, but an expansion. Einstein didn't kill Newton. He revealed a wider truth Newton couldn't see. If C ever turns out to be variable, it will likely come the same way. not as a single shockwave, but as a gradual accumulation of anomalies, each small but persistent, until the old theory can no longer carry the weight of evidence. That moment hasn't come, but that doesn't mean it never will. The cosmos is patient, and progress is iterative. The middle ground is where the real work happens. It's where new instruments are built, where models evolve to match narrowing limits, where theoreticians refine variability frameworks to survive new constraints. It's where astronomers look at gamma-ray bursts not with desperation, but with anticipation, knowing that the next generation of detectors might resolve details today lost in noise. Not revolution, but resolution. Not collapse, but clarity. If there is one mindset worth holding onto, it's this. Every time the speed of light withstands scrutiny, we learn. And every time we test the boundary again, we learn even more. Whether future data reveals constancy or cracks, both outcomes deepen our understanding of the universe. So let us neither cling nor reject. Let us observe. Let us measure. Let us keep the question alive, not as a threat to physics, but as fuel for it. Because the richest place to dig is exactly where certainty and mystery overlap, where answers tighten, yet the unknown still breathes. And that raises the most thrilling question of all. If the next breakthrough comes, what will it look like? What signal would finally break through noise so clearly that no one could ignore it? What would it take, truly take, to break the constant C assumption wide open? Not a hint, not a maybe, not a single burst with suspicious timing offsets. To overturn a century of relativity, the universe would need to speak clearly, loudly, repeatedly, and unmistakably. We're talking about smoking gun evidence, the kind that survives every counter-argument, every instrument check, every astrophysical uncertainty. If C varies, the proof must come not wrapped in ambiguity, but in patterns, consistent, reproducible, undeniable. One possibility is the cleanest. Multiple gamma-ray bursts from different regions of the universe and different epochs, all showing the same energy-dependent delay in photon arrival. Not random, not inconsistent. A repeatable trend where high-energy photons either arrive systematically earlier or systematically later than low-energy ones. Even after accounting for internal burst physics, source emission timing, and detector calibration. If 3 bursts show it, interesting. If 10 do, alarming. If 20 align with the same dispersion slope, the scientific world would feel the ground shift. That would be the moment where physicists stop asking whether C varies and start asking why, when, and by how much. But that would be only one pillar. A real revolution needs more. Another signal could come from gravitational waves, which travel through the same space-time fabric as light. Or perhaps not. If gravitational waves and photons emitted from the same event, like a neutron-star merger, arrive with different delays across multiple detections, and those delays scale with distance, we'd have evidence that space-time isn't treating all messengers equally. The 2017 event GW170817 already gave us a first comparison. Light and gravity arrived nearly together, but nearly isn't infinitely precise. Future detections at higher energies and deeper distances could sharpen that test. If the timing ever diverges beyond what relativity allows, even by milliseconds, that could be the crack. Then come high redshift standard candles. If quasars or supernovae at redshift 3, 4, even 8 show luminosity distance relationships inconsistent with constant C cosmology, while lower redshift data remains stable, we'd glimpse temporal variability. early universe physics refusing to match modern laws. A shift in brightness distance curves that cannot be explained by dark energy models, cosmic dust, or evolution of sources would push us into new territory, especially if the deviation scales smoothly with redshift, a sign that C drifted over time, slowly settling into the value we measure today. But even that wouldn't be enough unless cross-checks agree. GRB dispersion, gravitational wave timing, early universe cosmology, each must rhyme with the others. One line of evidence can be noise, two can be coincidence. But three independent methods aligning, science would no longer have room to hide. It would be the theoretical equivalent of triangulation. Light says it, gravity confirms it, cosmology maps it, and behind that moment, the world shifts. We must also consider anisotropy. What if variation shows only in certain directions of the sky? A cosmic dipole pattern where C is slightly faster along one axis of the cosmic microwave background and slower along another? If photon timing across bursts in different celestial regions converges on a directional bias, the standard model extension coefficients would light up like a constellation. That isn't random drift. That is structure, order, a signature in the very geometry of space-time. Directional Lorentz violation would be the kind of discovery physicists cannot ignore. Yet science demands one more layer: repeatability across instruments. A discovery isn't real until it's seen by Fermi, by CTA, by Imago X, by future MEVTV observatories, and not just once, but again and again, across years. Multi-wavelength verification, radio to gamma, multi-messenger confirmation, gravity and light, multiple redshifts, multiple sky regions. You need consistency stronger than skepticism, precision stronger than doubt. If that convergence happens, if the universe sends matching signals from different corners of physics, then textbooks won't just be revised, they'll be rewritten. Relativity won't die, but it will evolve, stretched to encompass a deeper symmetry or a broken one. The constant C universe would become a special case, not the whole story, but one chapter in a bigger book we are only beginning to read. And if those signals arrive, the shock will ripple beyond physics, into philosophy, into technology, into how humanity understands reality itself. So the real question is no longer, could C vary? But, if it does, what would that mean for everything built upon it? If the speed of light turns out not to be eternally fixed, it could be the first visible crack in the wall separating our current theories, relativity, quantum mechanics, the standard model, from the deeper framework that unifies them all. For over a century, physics has lived in a split brain state. Einstein's relativity governs the cosmic scale, bending space-time like fabric. Quantum mechanics governs the microscopic, behaving like probability waves and uncertainty fog. Elegant separately, incompatible together. The constancy of C has been the peace treaty between these two empires. Break that treaty, even slightly, and we may finally see how they merge. A varying speed of light could be the missing stitch in a long-torn seam. Imagine what that would mean. A new theory of quantum gravity, not myth, not math alone, but an empirically guided framework. String theory, loop quantum gravity, causal sets, emergent spacetime. Ideas once philosophical could become testable. If C shifts at Planck scales, then quantum foam, long treated as abstract speculation, becomes measurable reality. If C varied during the Big Bang, we might not need inflation at all. Early universe expansion might be reinterpreted through communication speed rather than cosmic stretching. dark energy, one of the deepest mysteries of modern cosmology, might not be energy at all, but an artifact of changing information speed over time. These questions are enormous, almost mythic, yet grounded in real data. That's the beauty of this frontier, and it goes further. If C is not constant everywhere, everywhen, or for every photon energy, then spacetime itself may not be a static arena, but a dynamic medium, evolving as the universe ages. Fundamental laws might not be eternal. They could be emergent, like ice from water, stable only within certain temperature and density ranges. The Big Bang could transform from a singular moment into a phase transition, where the speed of light, and thus causality, crystallized into something coherent. Before that crystallization, the universe might have behaved like a fluid without boundaries, faster communication, faster mixing, fewer fine-tuned parameters. Suddenly, the universe looks simpler, but stranger. Scientific revolutions aren't always explosions. Sometimes they are quiet, a narrowing of limits, a whisper of variation, a pattern emerging over decades until it becomes undeniable. The constant C debate may be that kind of slow earthquake. We may not notice the shift day by day, but in hindsight, historians might say everything began here, with astronomers asking whether one constant could flex. The next decades of research could transform physics, not through overthrow, but through extension. Einstein won't fall. He will grow. Relativity could become a special case of a deeper principle. The way Newtonian mechanics remains accurate for everyday speeds, but gives way to relativity at high velocity. And here's the thrilling part. This journey doesn't belong only to physicists. The public has always walked beside science when the biggest questions rise. People loved black holes before we imaged one. They debated multiverses before inflation made them plausible. They embraced quantum entanglement, while physicists still argued over interpretation. Curiosity is not academic, it's human. If the speed of light varies, even by a whisper, the implications belong to everyone who has looked at the stars and wondered how reality works. We may be living in one of those hinge moments, not the end of an era, but the beginning of the next. The universe is opening a door, and we are only just starting to step through it. The next discoveries will likely be incremental, subtle, not cinematic, but each one will push the boundary farther. That push is what science is. And if cracks continue to appear, if photon timing, gravity waves, early universe signatures all begin to align, then this debate may not just be a curiosity. It may be the seed of a new physics. Which brings us to the inevitable tension. Not everyone is convinced. Not every scientist is ready to follow this thread. And skepticism, sharp, rigorous, necessary, is part of the story too. Why hasn't physics already embraced a variable speed of light as the next great revolution? Because in science, fascination is never enough. Proof is the currency, and right now, variable C is rich in possibility, but poor in certainty. Many physicists admire VSL ideas intellectually, but admiration is not adoption. The community is cautious because extraordinary claims demand extraordinary evidence, and so far, the evidence for variation, if it exists, whispers rather than declares. Even the 2025 analysis, the strongest test ever run, is still a negative result, framed by improved limits. It says, "We don't see variation yet," not "variation is impossible." That is not a revolution. It is unfinished business. Critics point out that every potential signature of varying C thus far has an alternative explanation. Arrival delays between photon energies might be caused by internal emission physics inside gamma-ray bursts rather than propagation effects. Quasar-brightness relationships could be influenced by accretion disk evolution rather than cosmic geometry. CMB uniformity may be explained by inflation more cleanly than by VSL. Even gravitational wave timing differences could emerge from modeling assumptions or detector lag. For every trace hint that C might vary, skeptics can raise a simpler objection. Are we sure this isn't just astrophysical noise? Instrumental bias? A model we haven't corrected deeply enough? Until every alternative is eliminated, a variable speed of light remains a possibility, not a conclusion. There's also a philosophical caution at play, a hesitancy rooted in history. Physics has learned that beautiful theories can mislead, that elegant ideas can fail. The luminiferous ether was once beloved. Supersymmetry was expected at the LHC. Grand unification remains tantalizing but unverified. And right now, constant C still has sharper teeth. It predicts gravitational lensing, time dilation, particle accelerator behavior, cosmic expansion, GPS synchronization, all with extraordinary precision. If we replace that with VSL frameworks before evidence demands it, we risk breaking what works. This is why many researchers resist, not out of stubbornness, but out of discipline. Variable C may solve deep mysteries, but until we have a smoking gun signal, it remains a hypothesis trying to become a theory. The difference between those two is the difference between possible and proven. Science does not move because something could be true. It moves when something must be true. And constant C has not yet been overthrown, challenged, or forced into retreat. It continues to match every measurement we throw at it, surviving stronger tests with each passing year. As long as it holds, the burden of proof lies with its challenges. And that burden is heavy. Yet skepticism is not an obstacle, it is propulsion. Debate is not paralysis, it is progress. Physics grows by challenging itself, by grinding hypotheses against evidence until one breaks. The beauty of this moment is that nothing is settled, and nothing is dead. The constant C framework stands firm, but the possibility of variation remains unclosed. We are living inside the tension, the most fertile space in science. And as long as uncertainty exists, questions will continue, instruments will improve, and minds will push deeper. Which brings us to the simplest and most empowering point of all. What should you, as an observer of this unfolding story, carry forward from all this? When you step back from the equations, the telescopes, the gamma-ray bursts, and the debate, a simpler question remains. What does any of this mean for you? If you're not a physicist, if you're not spending your nights parsing SME coefficients or photometric timing errors, why should the constancy of C matter? Why should you care whether the universe whispers variation at the edges of time? Because what's really being tested here is not only the speed of light, it's the nature of knowledge itself. Science is not a monument carved in stone. It's a living process. A conversation with the universe, constantly revised, constantly challenged, constantly sharpened by new evidence. The fact that we question C at all means something profound. Even the rules we think are fundamental may still have layers beneath them. We do not live in a universe already solved. We live in a universe still unfolding. And that is thrilling. Even if this constant stands unbroken for another century, even if future instruments find no variation at any redshift, any energy, the act of testing strengthens physics. It proves we are not complacent. It proves we are willing to press against the walls of certainty and listen for echo. Scientific truths are not sacred by default. They are sacred because they survive challenge after challenge. If C withstands the next era of tests, then relativity grows stronger. If it buckles, then physics grows deeper. Either outcome advances us. For you, the viewer, the takeaway isn't C varies or C doesn't. The takeaway is never stop asking. Curiosity is not naivety. It is the engine of discovery. You don't need to choose belief or denial. You can hold space for uncertainty. You can watch this story develop like a cosmic mystery. You can understand that being open-minded doesn't mean accepting every claim. It means engaging with evidence, waiting for pattern, valuing skepticism and possibility simultaneously. That balance is what science is, and you are part of it. Because science isn't just something done by people in labs. It's a cultural movement of curiosity. It shapes the world you live in. The GPS that guides you, the communications satellites above your head, the lasers in your devices, the electronics in your pocket. All of them work because of light-speed constancy as we currently understand it. If that constant ever shows even a hairline crack, our entire view of space, time, causality, and origin could shift. Not in a way that breaks your everyday life, but in a way that reframes what everything means. And meaning matters. So keep your eye on the future, on the headlines about gamma-ray bursts, on new gravitational wave-light timing comparisons, on the next generation of telescopes that will stare deeper into cosmic history than humanity has ever seen. You don't need to memorize equations or analyze datasets. You only need to care that the universe still has questions, and that we are still brave enough to ask them. Because curiosity is not childish. It is civilization's most grown-up trait, and we're not done yet. Which leads us to the final stretch of this journey. Not an ending, but a reflection on where this story could go next. What happens if evidence emerges? What happens if it doesn't? And what might we one day learn from photons still traveling toward us across cosmic time? So here we stand. Not at an answer, but at a horizon. Will we ever know with absolute certainty whether the speed of light is constant everywhere, at all times, in every corner of space-time? Maybe, maybe not. The universe is not obligated to be simple, or generous, or legible to creatures like us. It doesn't hand over its secrets on command. It lets us uncover them grain by grain, photon by photon, over centuries. Some truths surrender easily. Others hide behind distances so vast we will never cross them, behind energies so immense we may never reproduce them, behind cosmic history so ancient we can only infer its whispers through fossil light. But instead of frustrating us, that uncertainty should humble us and electrify us. For now, C stands undefeated. Einstein's postulate remains the backbone of physics, the ruler by which space-time measures itself. Yet the room in which variation might hide has grown tighter, sharper, cleaner. Decades of gamma-ray bursts, reanalyzed through a unified lens, have narrowed the possibilities. If light speed wavers, it does so in shadows we haven't yet. Illuminated, at energies beyond our reach, in epochs before galaxies existed, or in gravitational realms too extreme for current instruments to probe. Constant C survives, not because we stopped questioning, but because we questioned harder than ever before. And the questioning is the point. The universe remains open, unfinished, a book with pages still being written in real time. Somewhere right now, photons are racing toward us from stars not yet born in our night sky. Somewhere, a gamma-ray burst explodes at the edge of time, sending a cascade of energies that won't reach us for 1 billion years. Somewhere, the answer may already be en route, encoded in light that has been traveling since before Earth formed. A deviation, a delay, a defiance, or perfect agreement to the last decimal, a cosmic yes to Einstein's intuition. We may not know today, we may not know in 10 years, but we will know more. And that is the beauty of science. We do not need certainty to continue. We need curiosity. We need patience. We need instruments sharp enough to test reality instead of assume it. What matters is not that C might change, but that we dare to ask whether it does. Because every time we push against the boundary of knowledge, the boundary moves. So let the story breathe. Let the question stay unsettled. Let us hold the unknown gently, not as a threat, but as an invitation. Because as long as we keep measuring the sky, as long as we keep building better instruments, as long as we keep wondering instead of concluding, the cosmos will continue to answer. And maybe, just maybe, the next photon that arrives will carry a surprise big enough to rewrite everything. The door stays open. The universe keeps speaking. We continue to listen. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.